So this morning I'll be talking about symmetry. First of all, the Center for Sacred Sciences has a mission, and it has three parts to it. The first part is to demonstrate that there's a common universal truth that's shared by all the major religious traditions. It's the part that's at the core of them, the mystical core of the great traditions. And this you're probably familiar with if you've been here before, as well as the second part, which is to foster a community of spiritual practitioners who want to enact them in their own lives and transform themselves. And we have various activities to support that, including practitioners, groups, and retreats. And most of these Sunday meetings are focused on these parts. There's actually a third part of our mission, though, which is to help develop a new worldview that will help show that both science and mysticism are different ways of understanding the same underlying reality. And just as the teachings of the mystics that relate to our own practices and transforming our own lives help relieve our suffering, this third part of the mission is more of a teaching on a societal level. You could view it that way. Is that the idea here is to present a teaching that may be relevant on a broader, more long-term scale, on a societal level. Our worldview informs how we, especially when we're raised, the kind of experience we have about the world, what we take for granted, and insofar as that worldview is not aligned with reality, we're going to suffer as a society. So if we can foster a worldview that is more harmonious, that helps present science and religion in a way that is more mutually compatible, our technological society will hopefully be more compatible with the teachings of mystics of the religions of the world. So that's part of the idea behind this third part of our mission, and I'm going to speak more to that today. So I'm going to start with this quote by Simone Weil, who was a French mystic, philosopher, and social activist who lived in the first part of the 20th century. Her brother, it turns out, was also a prominent intellectual, mathematician. And even though she wasn't a mathematician herself, she was very close to her brother, and she was exposed to a lot of very advanced mathematics that way. And she has this to say about this cube. We conceive ourselves of the reality of an object by going around it, an operation successively producing varied appearances which are determined by the immobility of form, which is different from all the appearances. So you'll see the appearance here of these lines, these blue lines, is changing. And the lengths of some of these lines are changing. Their angles are changing. You're not seeing the same thing from moment to moment. And yet, our minds imagine a three-dimensional cube there that is not changing. We imagine those sides to all be the same length, and the angles between those edges to be the same angles, and the size of everything to be the same. And it's only the appearances that are changing here. And so even though there's this variation of appearances, we imagine there to be an invariant form behind them somehow. And she says that these relationships can, by analogical transposition, furnish the key to the whole of human knowledge. There's great profit in meditating indefinitely upon these relationships. That's a pretty audacious claim, really. The key to the whole of human knowledge? Really? She was a mystic and a mystic philosopher, and she saw the profound nature of this concept of symmetry not only in philosophy, but she saw its connection with mathematics and science as well. So this is kind of the springboard for this talk on symmetry. What does she really mean here? Why is this such an important key to understanding everything? And why would it be so profitable to meditate indefinitely upon this? So first of all, what is symmetry? It comes from the Greek. The root of it is the same as the root of meter or measure. A thermometer measures heat. A meter stick measures things. So it's basically the idea is to measure. And sum means like. And so it's a similar measure. It's a like measure. So if you're measuring two things and you measure the same thing for both of them, then you have a like measure. For example, if we consider the letter H, if you draw a vertical line down the center of it and you measure both to the right and to the left of that line, you get the same measurement, the same distance, to each of the vertical bars on the H. So we have the same measurement on both sides. And as a result of that, if you flip it around, it doesn't change because it's the same measurement on both sides. So if you flip it, nothing changes. So there's an invariant there, even though we are changing it somehow, we're flipping it around, and yet it appears the same. So there's something that is invariant or constant, even though there's something that's changing. And that's because of this same measure on both sides of this axis. You could also draw an axis horizontally, and you'll notice that if you measure up and down from that axis, you get the same measurements to the tips of those bars, which means that if you were to flip it around that axis, it would look the same. So again, you can change it by flipping it or reflecting it, and yet it'll appear exactly the same. If I were to tell you all to close your eyes, and I'm going to either flip it or not, and then you open your eyes, and then I tell you, well, did I flip it or not? You couldn't say, right? Because there's no change in the appearance, even though I either did or didn't flip it, right? So we could also consider another axis. This is a diagonal axis, and you'll notice that you don't get the same measure to the different parts of the H from this axis. So if I were to flip it along this axis and ask you if I flipped it or not, you would notice. So this is not an axis of symmetry. So when we say that the H is symmetrical, it's not enough to just say it has symmetry. We need to say, well, it has symmetry along a vertical axis and it has symmetry along a horizontal axis. So we need to be a little more specific about what we mean. We have to specify the type of transformation with respect to which it is symmetrical. So let's just go through some examples here to help you get the feel for it a little more. So the letter A has a vertical axis of symmetry. If you flip it around that axis, it's the same. So does the letter T, so does the letter O, so does the letter M. So those are examples. Some letters that have a horizontal axis of symmetry is the letter I, D, E, O. Yeah, so if you flip all of those along a vertical axis, a horizontal axis, the appearance will not change. And you'll notice it's not just any axis about which you flip them. It has to be one aligned right down their center. So some letters actually have more symmetry than that. They have symmetry about both axes, as we saw with the H. So the X also has symmetry about both the vertical and horizontal axes. So does the I, so does the O, so does the H. Okay, so quiz time. What are the symmetries of this object? So you have these diagonal lines and these vertical lines. Yeah, so there are 1, 2, 3, 4 axes of symmetry. Any others? This is a trick question. So that I threw in something new here. This has what's called a rotational symmetry also, which is not the same as a reflection. And so you can rotate it 90 degrees, you can rotate it 180 degrees, you can rotate it 270 degrees, or you can rotate it all the way around, which is an interesting kind of symmetry because it's the transformation that does nothing. takes it to itself. Okay, so how about that axis? No. If you reflect it across there, you're not going to get the same image. Same with that one. It is a vertical axis, but it's not going through the center of the object. So if you flipped it, a bigger part of it would be off to the right than to the left, and it would still look the same, but it would be shifted, right? It wouldn't be in the same position. Yeah, there are various ways you could take it that aren't symmetrical. Here's another object. So it also has these axes of symmetry for reflection. If you reflect along any of these axes, it will be there will be no change at all in the appearance of the object. It'll look identical. If I flipped it along any of those axes with your eyes closed and you opened them, you'd never know whether I flipped it or not. Also, I could rotate it by 72 degrees. Or rotate it several times by 72 degrees. Or rotate it all the way around. And you would never know whether I rotated it or not. Okay. So those are different symmetries for this different object. And mathematicians sometimes actually describe objects in terms of their symmetries. They say, well, let's talk about all the objects that have this kind of symmetry. And they might that might apply to a bunch of different objects. And that's one way of studying them. Here's an example of a rotation that would not be symmetrical. It would take that top corner down to a place where there is no corner right now. So if I rotated it like that and asked you if I rotated it or not, you would say, well, yeah, it looks different now. Right? So it's not a symmetry. And that is another reflection that's a little bit off, right? It goes through the center, but it's not at an angle where a reflection would make it appear exactly how it appears now. You would know if I flipped it along that axis or not. Same with that axis. If I flipped it there, you would see it was a little shifted over to the right. So what are the symmetries of a circle? What are the reflection symmetries of the circle? You could reflect it along any axis you like, as long as it goes through the center, because a circle has that perfect rotational symmetry to it. Same with rotations. Any size rotation you like, as long as it's around the center, the circle will be unchanged. But if you reflect it across an axis that doesn't go through the center, then again you'd know it because it would have shifted to a different place. Or a rotation about another point that's not the center. We would know that it wasn't, that it was changed. So this is how I'll define symmetry. I'll say it's an object has a symmetry if there are ways to change it, such as reflecting it or rotating it, such that certain properties remain unchanged. So in this case of the square, the way we change it are rotating it around the center by multiples of 90, reflecting it along vertical, horizontal, or diagonal axes. And when we do that, there are several things that do not change. The position doesn't change, the size of it doesn't change, the orientation doesn't change, the shape doesn't change. All these things are invariants with respect to those transformations. What remains unchanged is always relative to what we're changing. So change and unchange, variation and invariance are these complements that play with each other in relationship. So there are different ways to change things, and there are correspondingly different invariants of those types of changes. So let me illustrate that with some examples. So if we only change the square by, say, shifting it and rotating it, then the position will change because we shifted it. If I move it to the other side of the screen, you'll know. And if I rotate it, you'll know. But the size of the square is invariant with respect to that. And the shape is invariant. It's still a square. It hasn't changed to a triangle or something. So there are certain things that remain unchanged when I change it in these other ways. And those are the invariants with respect to these variations. Now I can say, well, let's change it more. Let's change it in other ways and see what remains invariant. So I can translate it, and I can also scale it. So here I've made it bigger. And so the size is no longer an invariant. We only have the shape being the same. It's still a square. So here are these examples kind of all lined up. The bottom line here shows you that if we simply translate it, then the size, the shape, the orientation all stay the same. If we allow you to rotate it also, only the shape and the size stay the same. And if we also allow you to scale it, then only the shape is the same. And we could imagine even more general symmetries than this, where let's say we allow the shape to change. And you could say, well, what could be an invariant then? Well, maybe the color could be an invariant. We have different shapes, but they're all blue. So this idea of being able to change things and have something that remains unchanged or common to them all is really what's happening when we identify a class of objects as being the same type of object. So if I give you a ball and I say, here's a ball, you look at it and you say, yeah, that's a kind of ball. It's an instance of this general class ball. And if somehow this basketball that I gave you changed into a tennis ball, I'd say, do you still have a ball? And you'd say, yep, I have a ball. And if that changed into a soccer ball, you say, yep, I still have a ball. So it's changing. It's doing all these changes. The pattern on the surface is changing. The size is changing. But it remains a ball. And so this can change. It can go through all these transformations. But there's something common to them all. There's something behind those transformations, just like that rotating cube at the very beginning that Simone Weil was talking about. There's something behind those transformations that's invariant. And that's the fact that these are all balls. They all have a spherical shape. So that spherical shape is the invariant here. Here we have 3 clusters of red and blue dots. Can you guess the invariant here? These look different, like different clusters. They're arranged differently. Balls. They're all balls. That's one invariant. Any others? Yeah, they're both made of blue and red balls, so that hasn't changed. Let's see, there are 1, 2, 3, 4, 5, 6 blue in each cluster, and the number of red actually changes. So there are several invariants here. Even though the position of these balls is changing, each cluster is composed of balls, little balls. Each cluster has both red and blue balls. That's an invariant. And each cluster has 6 blue balls, even though the number of red balls is changing. And if you consider the blue balls to be protons and the red balls to be neutrons, you could think of these as nuclei of atoms. And in particular, these would be nuclei of carbon atoms. And these are 3 examples of carbon isotopes. So the most common carbon atom is the one with 6 protons and 6 neutrons. And we also have isotopes, carbon-13 and carbon-14, which is used for carbon dating. And those aren't nearly as common. They're in small fractions but they still exist. But the important thing, the point here is that we call them all carbon. Even though these different types of carbon have different numbers of neutrons in them, they are all carbon atoms. They all have 6 protons and 6 electrons orbiting around, and so they chemically behave the same since they have the same number of electrons. When we talk about carbon, that's really a kind of invariant. We're saying an atom whose nucleus has 6 protons, and the number of neutrons could vary. And so that's a way that you could vary the nucleus of an atom while leaving its atomic number that identifies that element invariant. So this whole idea of identifying different substances and distinguishing them from each other involves this idea of symmetry, that there's something that can change while something is invariant. And what's invariant is what we kind of latch onto as the identifying property of that. So here's another example of something changing. Obviously here we have a picture of the Earth, and the different portions of the Earth are exposed to light. I believe this was taken from a satellite in geosynchronous orbit throughout one 24-hour period. So you're seeing the Earth change from day to night to day to night. So the light on any portion of the Earth is changing. So what are some invariants here? Yeah, the Earth isn't tilting or anything while this is happening. It's staying where it is.
Color?
Shape. The shape. Earth stays a sphere, yeah. Another thing that isn't really visual, but with respect to time here, even though the light is changing, it doesn't go quickly once and then go slowly another time. Every period is the same. So it's repeating this cycle once a day, every day, and it's the same duration of time. And so there's a symmetry. This is a symmetry through time, which is different from what we've seen previously. These have been symmetries in space, how we can change things. This is more of a symmetry through time, where something is changing through time, but throughout that change in time, there is something that is constant, which is the period of the rotation of the Earth. So we have 1 day cycle here. You could also say that half of the Earth is always illuminated. You don't see it from this one angle, of course, but if you were to, say, look down on the Earth, you'd always see half of it illuminated. So here's another one. This is a planet going around the sun. Its position is changing as it goes around. And actually its speed is changing too. The planets don't usually follow perfect circles in their orbits. They're actually ellipses. And in the portion of the ellipse where they're closer to the sun, they go a little bit faster. And in the portion where they're farther away, they go a little bit slower. So you couldn't say the speed is constant here either. Any idea what are some invariants of this?
The shape of the orbit.
Yeah, so it remains an ellipse. The ellipse itself isn't moving. Anything else? Right, so the orbital period is the same. The year, in the case of the Earth that we call it, would be the same. So it goes around. If you were to start your stopwatch each time it went the furthest point down and below, you would notice that it takes the same amount of time to go around each time. Mm-hmm. Yeah, so the orbit, in addition to not changing its shape, it's not shifting around, right? The sun remains constant, yes. Right, so there are quite a number of invariants here. Now, there's one that I'm not surprised you haven't mentioned, because it took people a long time to figure this out, and it's quite subtle. And Johannes Kepler discovered this, and they named the law after him, which is that you'll notice these sectors in the orbit that form kind of, they're not exactly triangles, but they're called sectors in the orbit. And in equal times, the planet sweeps out equal areas. And that's Kepler's second law of motion for the planets. So when it's farther away, it's moving slower, but it's farther away, and so there's more area there. When it's closer, it's moving faster, but it has a larger angle that it moves through. And so he actually figured this out, that the area that it sweeps out, say per day or per any unit of time, is the same. And no one had figured this out before, and he actually computed this for the planets and figured this out, and it was quite remarkable that he was able to discover this law. about the motion of the planets. He was also the first one to realize that they were ellipses and not circles. So this is the whole solar system now. So we've got all the planets here. Mercury, Venus, Earth, and Mars are right in the center there, close to the sun in that little cluster that's wiggling around. They're so close to each other you can't discern them from each other. The ones you can see going around are Jupiter, Saturn, Neptune, Uranus, and dwarf planet Pluto. So we no longer have that the orbital period is the same because different planets are going around at different lengths of time. The size of the orbit isn't the same for all of them. They're not all inclined at the same inclination. Especially Pluto is quite tilted compared to the others. So we've lost a whole bunch of invariants. So the trick here is to seek what is invariant, what is still invariant amidst all of this variation. What is in common to all of this planetary motion?
They're all going around something.
The sun is an invariant. Any others?
Are they all ellipses?
They are all ellipses, yes. That's something they all have in common.
Is the speed that they're moving relative to the size of the orbit?
Close. That's actually Kepler's third law, which is that, get this, the square of the period is proportional to the cube of the size of the orbit. So that is an invariant, and what's remarkable is that that ratio is true for all the planets going around the sun. So if you were to take a new planet and just throw it into our solar system and it started going around, the length of its year, the orbital period, if you square that and divide it by the size of its orbit, you'll get the same number as you would for doing it for any other planet. So every planet, if you square its period, divide by the size of the orbit, you get the same number for every planet in the solar system. And so this is pretty remarkable. It's a symmetry that isn't at all obvious to us, and yet he was able to discover this deep symmetry, this invariant amidst all of this variation. And this is really what discovering these physical laws are about. It's like we have all of this variation going on in the world around us. What is invariant in all of that? What is kind of tying it all together? What's a deeper principle that applies to everything throughout this change? And the way physicists work with this and discover these kinds of laws, like the square of something over the cube of the other, they have to start using mathematics here. There's no other way around it. You can't just, flip your square and discover something like this. You have to start making measurements and comparing numbers and things like this and discovering these mathematical relationships. So let's just get a feel for how this connects with symmetry, writing down these equations. If you imagine, let's say this is an object moving along through space, these blue dots, and they're moving along a line. So what's changing here is the position of this blue dot. So what is invariant here? How can we describe this mathematically? So we can say, well, it follows a line, but to express this mathematically, we need to use some numbers and find relationships between numbers to get an equation for this. And so we could put a grid over this, and what we notice is that for each successive position, you go over 2 and up 1, over 2 and up 1, over 2 and up 1. And so no matter what, even though there's this variation, there's this invariant here that always, for the next position, you go over 2 and up 1, over 2 and up 1, over 2 and up 1. So that's something that's in an invariant pattern throughout all of this motion. And you can actually write the numbers out and say, well, here the ratio of its vertical distance to its horizontal distance is 1/2, and there it's 2/4, and there it's 3/6. And 1/2 equals 2/4 equals 3/6. So you have the same number, just like Kepler had that same number for all the planets, with the square of the period over the cube of the size. So this is the same number, 1/2, for all those positions if you take the one distance and divide it by the other. So this can give you a feel for how these mathematicians and physicists figure out these invariants from making measurements. This is the equation that they would write down. You might recognize that from high school algebra. Y equals mx plus b. So the invariant there is the m and the b. In this case, the b is 0. It goes through the origin. But the m would be the 1/2. It relates all the x values to all the y values in a fixed way. So that's the mathematical invariant here. Now we'll get a little more complicated. Consider a parabola. What's the invariant here? Well, it's not quite so simple. You don't just have the same distance over and up, over and up, over and up. You have to look a little bit deeper. So if you have a ball moving along this parabolic line, what do all those positions have in common? What's the invariant behind this motion? Well, again, if we lay out a grid and make measurements, and we have this special point in red called the focus. And it turns out that this is a special point for any parabola. And what's special about it is that for any blue point along the curve of the parabola, the distance from that blue point to the red point, which is the red line, is equal to the distance from the blue line to the bottom, the horizontal line here at -1. So the green line and the red line are of equal length. And that equality is the same for any blue. You don't have the same length, obviously, but the fact that they're equal remains the same. You could say the parabola is the unique set of points for which the distance to the focus is the same as the distance down to that horizontal line. And if you said that, I'd say, well, you're talking about a parabola. That's the unique set of points that have that invariant property. So the variation here is the movement along this parabolic curve, and the invariant is, as I was saying, the distance to the point and to the line is always the same for all of those points. So this is leading somewhere, I promise you. So this is supposed to be, it's really close to a circle, but it's supposed to be an ellipse that's a little bit oblong. So the width here, I think, is a little bit larger than the height. Can you see that? So if we lay a grid over this and make some measurements, what is the invariant here? Well, it turns out that there's not one special point, but two. There's no line in this case. So instead of a point and a line, there are these two special points. And for any blue point on the curve, the sum of the green and red distances is always the same. So if you go around with the blue dot and you measure the distance to the red and to the green and you add them up, you'll always get the same. You can imagine this by tying a string, two ends of a string to the green and red dots. If there were pins in a board and you tied the ends of a string to the two pins and pulled it tight with a pencil and started going around, you would make an ellipse. Because the length of the string is always the same, and it's always going to be the sum of the two parts where your pencil's going. So that's the invariant for an ellipse. And so the mathematicians can look at this and see the variation of a motion, like, for example, a planet is moving around in an ellipse, and when we say, well, the shape is the same, it's an ellipse, you could also say that the distance the planet has between these 2 points is, if you add them up, it's always the same. That's an invariant. And that's another way of saying it's an ellipse. But it's a more mathematical way of saying exactly what an ellipse is How do you actually define an ellipse? You can define it by saying it's the set of points that have this property. So this is the invariant behind this variation of motion. So now we're to gravity and Newton. We're looking for a deeper symmetry here now. As I said a moment ago, if you throw an object into the air, you can throw it at different angles, and the path it follows will be a parabola, and the path that a planet follows around the sun will be an ellipse. Newton said, well, what is invariant between these two types of motions? You could imagine taking an object and throwing it up, it comes down in a parabola, and if you threw it hard enough, it would go up into orbit and it would go in an ellipse. And so something should connect these to each other. And what's the invariant behind this variation? We've got parabolas, we've got ellipses. And he discovered gravity, and he discovered these laws of gravity, which are equations that are much, much deeper than just the equation for a single parabola or the equation of a single ellipse. They're even deeper than Kepler's third law, which applies to all planets in the solar system. And so it turns out that you can take these general relationships he found, and you can say those are invariant with respect to all kinds of motion. Any motion you're talking about. It could be a projectile on Earth, it could be a planet going around the sun, it could be anything. And you set it up so this is an invariant with respect to all these different systems on Earth, in the heavens, and everything. So it was a deep and profound insight into something that is even more invariant in our world than any of the particular invariants. So we can see these kind of levels of invariance. We have Kepler's laws that apply to the solar system, and then Newton's laws that apply to not just the motion in the heavens, but also the motions on the Earth of projectiles and things. That's a deeper symmetry. And then Einstein discovered a symmetry even deeper than that goes even farther. And so the historical progression of physics, you can imagine as the quest to find deeper and deeper invariance amidst all this variation in the world. Turns out when you study the motions of the planets and larger objects like projectiles and stuff, things fit together very nicely. When physicists started looking at atoms, the laws of Newton broke down, and physicists had to discover a new set of laws. And this is Schrödinger's equation at the top, and it's an equation that describes the invariance as well over a very broad range of phenomena. And so it's able to encompass Newton's laws of motion as well as the phenomena of atoms. And the picture here, these are the different probability distributions of the electron around the hydrogen atom. So if you take a single proton and a single electron, you get a hydrogen atom, and depending on how much energy the electron has, it will exist in higher or lower energy levels. And those aren't properly conceived of as little planetary orbits on the atomic scale. It's not like that. Instead, these electrons are really better thought of as probability clouds. And they have these different distributions like this. And each one of these is a solution to this equation. Just like if you took Newton's laws and you solved it for the solar system, you'd say each planet, each ellipse is a solution to this equation. So these are the different patterns that have different energies corresponding to them for the single electron going around a single proton in the hydrogen atom. So that's what's remarkable about these deep invariants. Like the one equation for the ellipse resulted in all those different points going around, and a point over here is very different from a point over here. And what ties them all together? It's not immediately obvious. That equation is a fundamental law of physics, and it's an invariant. It's an invariant, yeah. So which means that every system this can describe, it's an invariant across all systems at all times. Yeah. So yeah, these laws of physics are really these very, very, very deep symmetries that physicists have managed to figure out are invariant with respect to all systems, all physical systems, in all their different configurations. They will all of them will have their properties satisfy this relationship. Just like for an ellipse, all the points will satisfy that relationship. So what we've talked about so far are particular geometrical symmetries and their invariance, particular symmetries of physical systems and physical laws, and you might say a deeper symmetry than that are some symmetries that are really axioms of science itself. So these aren't particular symmetries of scientific laws that I'm going to mention now, but rather symmetries of science, the very axiomatic ways that the way we define science, really, some of the fundamental requirements of science. One is that experiments need to be reproducible. If you can't reproduce your experiment, you don't call it a scientific experiment. It's not satisfying that requirement. So that means that if I do an experiment here today, someone else can go over there tomorrow and do a similar experiment and get similar results. It can replicate it or reproduce it. So that's a change through time and through space, and also through the experiment won't be exactly the same, but it will have to be set up to measure the same thing. For example, if you want to measure, say, the freezing point of water, we have to say, well, we have to agree to use the same kind of thermometer, calibrate it the same way, and we're going to both measure in Fahrenheit. All of this has to be agreed upon. So we have these parameters for doing our experiment. But then the basic idea is that within those parameters of the experiment, we can change its place, change its time. It shouldn't matter who's doing it. You should be able to come up with the same result, that it freezes at 32 degrees. So that's a fundamental requirement of science itself, and you can think of that as a symmetry, that it's requiring this same thing, namely the same results, have to be invariant with respect to these changes in time and place and experimenter. So the very definition of science itself has this kind of symmetry built into it, this requirement that you can think of as a symmetry. Another one is that the properties that science measures of systems really require that they don't depend on what's happening in the rest of the world. So if we're going to measure the freezing point of water, if that were to depend on what's happening in the Andromeda galaxy, we would be out of luck, because if that's going to depend on all these other things that we have no idea about and can't control or even measure, then we're not going to get reproducible results at all. So we have to assume, for the sake of doing science, that this is the case, that what we're going to be looking at when we do science is these properties of a system that are quasi-isolated, that aren't going to depend on random things happening in other parts of the universe. In other words, we're going to assume that our systems can be, relatively speaking, isolated from the rest of the world, the rest of the universe. And this is an assumption. We're not saying that this is true about reality or something. This is just one of the assumptions that science makes. It says, well, if we're going to study the world this way, this is one of the things we have to assume, really. And you can think of this as a kind of symmetry. There's an invariance here, namely that the observable properties of a system don't depend upon all these other variations that might be going on that we actually don't have any idea about. So the Andromeda galaxy might be doing this or that or the other. It doesn't matter. We'll still measure the same 32 degrees for the melting point of ice. So the other assumption is that what we're measuring is what are called objective properties of the system. if we are going to measure the melting point of ice, and each time we do it, it's different, even if we're not moving through time or space. Well, we have to move through time. There's not really a choice about that one. But if it's always coming up different, then it's going to be hard to find a lawfulness there. So to some extent, we have to assume that they're quasi-isolated from us as well. So we have to assume that our action of measuring the melting point of ice isn't going to change the melting point of ice. That's something that somehow is an objective property of the world. So that's part of the definition of what science is set up to look for. So these axioms of science are really looking for these kinds of symmetry, and it's saying that this is what the program of science is about. It's going to look for these symmetries, and here are the kind of filters we're going to put on. We're going to filter out everything that isn't reproducible and everything that isn't that depends on what's going on in the Andromeda Galaxy non-locally, and we're going to filter out what is influenced by us. And quantum theory has come up against this barrier. It's found some of the limits of this assumption, where the influence of the experiment does have an effect on what's measured. And so you start to see that the distinction we made here isn't a real one. Ultimately, there is a continuum, and we can't avoid but to interact with the world that we're measuring. So if I take a thermometer and put it in a cup of water, the thermometer itself is going to change the temperature of the water a little bit. So we have no choice but to interact and disturb something that we are measuring. There will be these variations that are unavoidable, but the idea is to isolate them and identify them and take them into consideration as much as possible. Because if there are too many extraneous random influences, we won't be able to discern any patterns to what's going on. So that's the end of the science part of this. Now we need to relate this to the mysticism part of this. So this is Franklin Merowolf, one of Joel's teachers. And in a talk he gave called the Yoga of Knowledge, or Jnana Yoga, he said this: having established a basic philosophic orientation, the sadhaka, which is the spiritual seeker, is now admonished to find the permanent in the impermanent, or in more modern terms, the invariant in the midst of all variation or becoming. This involves a directing of the attention and aspiration away from process, away from changeableness, and a directing of it to that which is persistent, and seeking there security. So, connecting this whole idea of symmetry and the seeking of deeper and deeper invariance of the world, you might say mysticism is taking this all the way ultimately, way beyond where physics could ever go, to the ultimate invariant of everything. So what is this? This is really a koan, is what is the ultimate invariant within all change, within all experience? What is it that never changes?
Is that what Einstein was trying to find when the one thing that was?
Well, within physics, they want to find the deepest invariant in terms of a mathematical equation for physical systems, but this is going way beyond what physics.
Einstein never did accomplish.
He didn't find his unified theory, unfortunately for him. So this is the mystical invariant, you might say. And for Dr. Wolff, his terminology for this was the transcendental subject to all experience, which is the invariant common to all variation. All of these phenomena and objects arise and come and go, planets, atoms, everything. The laws of physics could come and go. And the invariant to all of that in experience is that it is in consciousness, that there is subject to consciousness. That's awareness, you might say. And this is the ultimate invariant that the mystic is seeking. He also wrote what he called aphorisms of consciousness without an object. And in these aphorisms, he discusses this as well, and this dialectic where there's the balance between these different opposites, which are change and changelessness, time and timelessness. And here's the portion of the aphorisms where he discusses time and timelessness, or variance and invariance. And his term for the ultimate reality is consciousness without an object. He says, within consciousness without an object lies the seed of time. When awareness cognizes time, then knowledge of timelessness is born. To be aware of time is to be aware of the universe. And to be aware of the universe is to be aware of time. To realize timelessness is to attain nirvana. But for consciousness without an object, there is no difference between time and timelessness. So normally we're born into the world under delusion, thinking that our objects like chairs and rooms and planets are objectively existing. And sadhaka is admonished to seek the invariant. So the chairs and everything is impermanent. It's subject to decay, and in a more immediate experiential level, it's constantly changing. Just as that cube of Simone Weil is rotating, it's constantly changing. So it's to seek the invariant, and this is what physicists do with the physical world to a limited extent with their equations, but the mystical aspirant is admonished to go way beyond that, to leave behind concepts altogether, to seek the ultimate invariant of all experience. To go beyond all of time, the category of time altogether, to seek timelessness, and to realize that as an antidote to the attachment to these temporal objects. But then he says, don't get stuck there, because the ultimate reality embraces both. That's his last line there. The consciousness without an object transcends both time and timelessness. Here we're getting to the edge of where language can describe anything, but symmetry starts to give a flavor of how this can start to manifest conceptually. So there's a very profound philosophy in Buddhism called the Middle Way, where they teach that one shouldn't cling to either of two extremes. One shouldn't deny that things are totally distinct or deny that things are totally identified with each other, that there's a kind of play in reality between simple identification of everything or actually saying that things are really distinct from each other. Distinctions are real. This is not that. Clinging to that is also another extreme. But you could say symmetry is in between these two. It's this middle way where there's a play. You might say that what's happening between these two extremes of unity and diversity is a unity in diversity. And you might say that reality is the invariant with respect to distinctions. So you can make distinctions, whether they be distinctions in time or space or anything else. Those are imaginary distinctions and they arise, but reality itself is the invariant. It's unchanged with respect to those transformations. So this is really the ultimate. You could conceive of this as kind of the ultimate invariant. You can see this expressed if you conceive of this as the one and this is the many, the everything unified and everything distinguished. Nagarjuna said, without the one there cannot be many, and without the many there cannot be one. Therefore, one and many arise dependently. So clinging to just one as really being the case is not the truth, or the other, that they arise interdependently upon each other. Proclus, who was a Neoplatonic mystic, said the cosmos is not a unity here and a plurality there, but a unity and a plurality at the same time throughout its whole being. And Plato said the one and the many run in and out of every word that is uttered. So at the one extreme down here, we have the many, and if you say that everything's ultimately distinguished, there's nothing to connect them or to find an invariant among them. If you say that everything's just a one, then there can be no symmetry then either, because you have no possibility of transformations. So in between these two, you have increasing symmetry and decreasing symmetry, all these different kinds and levels of symmetry. So what we're touching upon here is a way of, to the extent possible, understanding the laws in which things appear to manifest. So using these, as Simone Weil said at the beginning, we can contemplate this, and it will be a key to help us understand all of human knowledge. There's unlimited value in contemplating these things, she said. So maybe you'll be drawn to contemplating these or not, but in any case, I hope there's been something here that might be of value to you, and it might give you a little bit of a sense of how some of these mystical teachings might be able to relate to science and mathematics in the way that they formulate the laws of this universe. Thanks for your attention.